Chapter 28 is the first of the two big statistics chapters, and we're going to start out with some vocabulary matching here. And here are three terms that I'd like you to take a second and match up with the definitions, or try to. So pause the video and give that a try. Okay, first off, a random variable is the number form of the possible outcomes which could occur for some random experiment. So it's the thing that's changing from one outcome to the next. A discrete random variable is something that is countable. For instance, the number of houses or defective light bulbs. You can physically count those. And a continuous random variable is something that can be measurable. For instance, the heights of men or the amount of rain. It's something that you can measure, and it could be any number, but you measure to find it, as opposed to counting. So a probability distribution is denoted by one of these three things where x is the random variable. An example here is tossing two coins. The random variable might be the number of heads that we get. So the possibilities for x are x equals 0 heads, or another possibility is we get 1 heads, or we could get 2 heads. Those are all of the possible values that the random variable could take on. And the associated probabilities, we could make a quick list here, or a tree diagram. We could get heads, tails on the first coin, and heads, tails on the second coin. And the probability of getting a 0 is 1/4. Probability that we don't get any heads. Probability that x equals 1, that is we get 1 heads, is 1/2, and the probability that x equals 2, that is we get 2 heads, is also 1/4. And sometimes these probabilities are shown with something called a spike diagram, or sometimes a histogram. Bar graph. This is an example of a bar graph showing the different probabilities for each of these values that the random variable can take on. We'll look at a spike diagram in one of the upcoming examples. A big property of a probability distribution is that all of the probabilities have to be between 0 and 1. That should make sense. And all of the possible outcomes, their probabilities have to add up to 1. Something has to happen every single time. That's what this is saying. So here's an example. Magazine store tells us what percent of the customers purchased how many magazines. The random variable in this would be the number of magazines purchased. And the possible values it could take on are 1, 2, 3, 4, or 5, or technically people could buy 0, but nobody bought more than 5. And we want to make a probability table for the random variable. So the probability that our random variable equals any one of these x values. And these probabilities are given to us in the problem. We don't have anybody purchasing the first, or we don't have anybody that bought 0 magazines. 23% bought 1 magazine, 38% bought 2, 21% bought 3, 13% bought 4, and 5% bought 5. Is this a probability distribution? What we have to look at is whether or not these probabilities add up to 1. And if we add them, they do all add up to 1, so this is a probability distribution. Now we want to graph this using a spike diagram, or a spike graph. It's very similar to a bar graph. The probabilities go up the vertical axis, the random variable goes on the bottom, and what we're going to do is we're going to put a dot at each probability. So 0.23 would be about there, 0.38, 0.21, 0.13, and 0.05. And the reason it's called a spike diagram is, or a spike graph, is we put each of these points on a spike. There's our spike graph. Here we want to find the probability distribution of our random variable. That is picking the number of reds selected. Well, we're picking 2 marbles, so the possibilities that x could take on are 0, 1, or 2. And to find this probability distribution, that is to find the second column, to find the probabilities of each value of the random variable, probability that our random variable x takes on each of these values, we can make a tree diagram. We could pick a red or a blue. Probability of getting a red is 2/3. Probability of getting a blue is 1/3. And on the second pick, we could get a red or a blue again. On this first branch of the tree, picking another red, the probability of that is 3/5, 2/5 for picking a blue. On the second half of the tree, 4/5 picking a red, and 1/5 picking a blue. So the associated probabilities, getting 0 reds, that would be a blue and a blue, that is 1 out of 15. Getting 1 red, that would be a blue red or a red blue. We have 4/15 here and 4/15 here for a total of 8/15. And then probability of getting two reds is a red red, so that is 6 out of 15, or that one could be reduced to 2/5. But if you add these up, you notice they add up to 1. This is our probability distribution. So now we have a spinner labeled 1, 2, 3, and 4, and we win money according to this table. And we're going to look at something called expectation, or expected value. The way we calculate expected value is we take each probability times the outcome, and we add up those products. So to find our expected value, where our random variable x is the different outcomes, that is winning $1, $2, $5, or $8, there are 4 values that our random variable can take on. We're going to take the probability of each of those times each value. So the probability of winning $1 is 1/4. We're going to assume that this is a fair spinner, times the outcome, 1, plus 1/4 times the second outcome, which is 2, plus 1/4 times the third outcome, plus 1/4 times the fourth outcome. So our expected value is equal to $4. And then I can pose the question, would you recommend playing the game if it costs $5? Well, mathematically speaking, no, I wouldn't recommend it, because we would only expect to win $4 in the long run. If we played for a very long time, math says that our winnings and losings would balance out to $4 per game. But we're losing $1 each time we play then. So it wouldn't be a good game to play. Definitely favors the house. So here's the assignment for the first 3 sections.